Hi everyone. So in today's video, I'm going to go over this paper, Open Reasoner Zero, an open source approach to scaling up RL on the base model by Jingsheng Hu, Yin Zhang, Shi Han, Daxin Xiang, Shanqiu Zhang, and Yong Yong Shong from Step Fund and Tsinghua University. I'm really sorry if I mispronounced any of those names. I have like a curated reading list for reasoning models and I'm trying to cover them sequentially. I made a video about DeepSeek a while back, and yeah, I just want to now read all of these. And if you have any more suggestions, do let me know. Right. So they introduced Open Reasoner Zero, the first open source implementation of large scale reasoning oriented RL training, focusing on stability, simplicity, and accessibility. Through extensive experiments, we demonstrate that a minimalistic approach vanilla PPO with GAE, Lambda 1, and Gamma 1, and straightforward rule-based rewards without any scale regularization is sufficient to scale up both the response length and benchmark performance, similar to the phenomena in DeepSeek R10. All right. Using the same base model as DeepSeek R10 Qwen32b, our implementation achieves superior performance on AIME 2024, Math 500, and the GPQA Diamond benchmark, while demonstrating remarkable efficiency, only requiring a tenth of the training steps. In the spirit of open source, they also release everything. Okay, so let's see. This is Open Reasoner 07b, Open Reasoner 032b on AIME. Okay, this is the ceiling set by DeepSeek, and this is QWQ32B preview. Okay, yeah. So they use the same model as Qwen32B. As like DeepSeek R10 Qwen32B, which is I guess built on top of Qwen32B. Yeah. Introduction, large-scale RL training of LMs on these tasks has emerged as a promising paradigm. Recent breakthroughs like O1 and R10 have demonstrated remarkable training time scaling phenomenon as the training computation scales up both the model's benchmark performance and response length consistently and steadily increase without any sign of saturation. Inspired by these advancements, we aim to explore this new scaling phenomenon by conducting large-scale RL training, even applying it directly to base models. An approach we refer to as reasoner zero training, which is essentially, if you remember the original DeepSeek, uh, R, yeah, the DeepSeek P3 R1 paper, they have like this R10, which is running pure RL on a base model, I presume, instead of first like having doing some cold start fine tuning to like teach it to reason. In this work, we introduce Open Reasoner Zero, or the first open source implementation of large-scale reasoning-oriented RL training on LLMs, with our best practices designed to be robust, scalable, and simple to follow. Under this paradigm, LLMs are trained to master diverse reasoning skills under verifiable rewards, spanning arithmetic, logic, coding, and common sense, like scientific problems, numerical reasoning, natural language understanding, and even creative writing. While DeepSeek's R10 outlined a training pipeline briefly, provide a comprehensive study of our training strategy with in-depth insights into overcoming common challenges such as training instability, stagnating response rate, benchmark performance plateaus, and reward design. Our goal is to democratize advanced RL training techniques to the broader research community. Okay. Our proposed Open Reasoner Zero outperforms the DeepSeek R10 with the same Qwen32b based on these datasets, yet only 1 by 10 the training steps. Very cool. Through extensive evaluation studies, we summarize some key findings and lessons learned. Specifically, vanilla PPO using GAE, Lambda 1, Gamma 1, and without any KL related regularization, combined with straightforward rule based reward, is sufficient to achieve steady scalability in both response and benchmark performance across varying model sizes and training data scales. This stable scaling resonates well with the bitter lesson. The most significant performance improvements stem from the scale of training data and model size and iterations rather than complexity of design choices. The most critical thing is how to design a simple and effective RL algorithm to scale up the process. They release all training resources, including code parameters, data, and model weights. We're excited to share this breakthrough of scale up RL. They've repeated this multiple times by now. This empowers. They also provide recommended practices for half B and 1.5 B models. These are the contributions. I know them by now. Findings indicate that model performance continues to improve even with more training, showing no signs of saturation. In light of this, we are releasing our training data sets. Uh, okay, yeah, standard stuff. So the amount of reward it gets seems to be stagnating, but the response length, yeah, I don't really know what's happening. Why is there like a peak and then this fall and then a peak and then a fall? And yeah, yeah. Interestingly, the response length exhibits fluctuations without negatively impacting training stability, highlighting the robustness of memory industry recipe. I would, yeah, I don't really know how to think about these peaks, but maybe after reading the paper, I have a better idea. Okay, scale up RL from a base model. In this section, they describe the strategy. First, they introduce the basic yet critical setting for a scale up RL training from a base model, data curation, reward function, PPO settings. Okay, basic setting. They conduct experiments using Coin 2.57B and 32B as a base model and directly starting the large scale RL without any fine tuning like distillation or SFT. So this is like not no cold start or anything, just base model RL. Building upon these base model, they scale up the standard PPO algorithm with scalability and robustness considerations. Our training data comprises tens of thousands of carefully curated star questions. Okay, inspired by R1, we design a template to elicit inference computation, gradually mastering the reasoning ability. Furthermore, we develop an efficient and easy to use large scale RL training framework based on OpenRLHF by introducing a more flexible trainer engine with GPU collocation generation and training with offload and backload support. Okay. What? Yeah, this part seems quite interesting. I would. Mm, yeah, I'm not connected to the internet right now. Uh, Maybe I should have before starting the recording, but okay. I can't look at the code right now. Data set. In this section, we introduce our carefully curated data set detailing the sources. So they collect public data set, AIME, Math, Numina Math, Lulu 3 Math, OpenR1 Math, and other open source datasets based on source and problem difficulty. We retrieve AMC, AIME, Math Olympiads, and Art of Problem Solving Forum components as our difficulty level prompts to ensure appropriate difficulty levels. We synthesize additional reasoning tasks using programmatic approaches. Okay. We exclude problems that are challenging to evaluate using rule-based reward functions such as multiple choice and proof-oriented. We implement model-based. Okay, so this is not model that is then I guess not good at proofs. We implement a model-based filtering strategy based on heuristic evaluation. Specifically, we use LLM to assess the pass rate of each problem, removing samples with either too high or zero pass rates. Okay, this I think both of these are interesting points too. Uh, this is when my yeah perfect behavior aim for like absolutely perfect behavior kicks in and try to highlight the same thing. uh, in good ways. The final, so they only have 129K samples. So I mean, it's not only, but it's not a lot. Additionally, we leverage the training process of our Shadi2B model itself to identify challenging and high quality prompts. They initially trained this model for 1100 steps. Subsequently, they pinpoint particularly difficult prompts uh, defined as those where the model achieves fewer than 4 correct out of 64 attempts. They get 30,000 challenging prompts. These identified prompts are then selectively used in the final stage training of 100 additional steps to improve the model on those things. Makes sense. Yeah. In the future, we aim to expand our data set by standard stuff, and they use Math Verify for their correctness. All right. And let me quickly look at the prompt. template for open region 0, prompt will be replaced with the specific question. A conversation between user and assistant. The user asks a question and the assistant solves it. The assistant first thinks about the reasoning process in the mind, then provides the answer, provides the user with the answer. The reasoning process and answers are encoded within the think and answer tags, respectively. That is think reasoning process here, answer here. User, you must put your answer inside answer tags, that is answer here, and the final answer must be extracted automatically by the this box tag. And then prompt, and then you prompt it with the think tag at the start so that it thinks. Okay, looks cool. Now, the reward function. Unlike DeepSeek R10, our scale-up RL training employs a simple minimalist reward rule-based reward function that solely checks answer correctness without any additional format rewards. Specifically, this reward function is designed. Okay, oh, so there's no format rewards. It's designed to extract the content between answer tags and compare it with the reference answer. To maintain clarity and simplicity, there's a binary thing, 1 or 0, and to have a good evaluation, they use Math Verify. I think Math Verify is by Hugging Face, if I'm not wrong. Yes, Hugging Face. Uh, Surprisingly, we found that a designed prompt, with a designed prompt, even unaligned base models can yield well-formatted responses in high probability. Then, during early training stages, the base model can quickly learn and reinforce the correct format for raising an answer incentivized by a simple rule-based reward. More importantly, our preliminary experiments revealed that complicated reward functions were unnecessary. Okay, this is interesting as well. What's figure 4? Okay. Percentage of response following the reasoning format. Results demonstrate rapid adoption of structured reasoning patterns even by base models using only a simple rule-based reward. So for 7B starts off, I guess, at a lower point than 32B, but within 100 steps they get like close to 100% following, which is very nice. Okay, now there are algorithms. We adopt the PPO instead of GRPO, which DeepSeek R10 does. Specifically for each question that is prompt, the model generates a group of responses and receives corresponding rewards based on the rule-based reward function where n represents the number of trajectories. For each response, OI at time step t, that is token t, let ht denote the state at time t, which comprises the question and all previously generated tokens, and AT denote the token generated. They compute advantage estimation for each token using generalized advantage estimation GAE. This is like very standard PPO stuff. Generally, GAE provides a trade-off between bias and variance in the advantage estimation by combining multiple in-step advantage estimates to an exponentially weighted average controlled by parameter lambda. So your advantage is computed as delta t, which is essentially your, I guess, temporal difference thing with gamma and lambda. So this is just like weighing it for basically down weighing your future rewards and focusing on immediate reward. And this is like your horizon. But if you remember, gamma and lambda were one, so you weigh everything equally, essentially. Where delta is your reward plus your value function at the next state, like a discounted value function minus your value function at the current state, which is like the temporal difference residual. Gamma is a discount factor that determines how much future rewards are valued relative to immediate rewards. The PPU algorithm updates the policy model parameters theta to maximize the expected reward and value model parameters phi to minimize the value loss by optimizing the following objective. So you don't want to take very big steps, which is why you clip it to some epsilon bound. And then you want the action to become more likely under the new policy as compared to the old policy. And then, yeah, epsilon is a clipping parameter, pi theta is current policy, pi theta old is old policy, under which you sample the trajectories, I believe. V phi is the value function, and this is the discounted return. We instantiate the PP algorithm with carefully tuned hyperparameters. GAE lambda 1, discount factor 1, clipping 2.2. So this is interesting. So they're essentially weighing the current token the same as any future token, which I think I've not seen very often. And then I am not fully sure how do you read out the sample, but this just looks like an estimate of the expected value. Uh, okay, no, I'm not fully sure what this represents. Do they refer to equation 2 anywhere? Uh, so this is, oh, sorry, I've messed up. So this is the thing for model parameters, and this is for the value model parameters phi. So you want its value, like the value function that it estimates for any given state, to be very close to like the actual reward you get at that state, like the actual return you would get from that state, the actual discounted return, and this is like the expectation of it, and then you want to, I guess, have very little discrepancy between the two, so you want to have this as low as possible. Key findings in the study: we explored best practices for reasoning-oriented RL training. We did an emphasis on stability and scalability. We conducted extensive experiments across the design space. Here are the key findings. First, you have RL algorithm key implementation details. They find that vanilla PPO is remarkably stable through extensive experimentation. They find that the advantage estimation parameters play a critical role. Lambda 1, gamma 1 is quite good. We show that simple rule-based reward function is not only sufficient but optimal, as minimal design leaves no room for potential reward hacking. Uh, we show that simple rule-based reward training is not only sufficient but optimal, as minimal, yes, notably even unaligned based models quickly adapt. I also wonder how much of this is just like a Quen model specific thing, because I've seen like some work by I think it was Luke Settle-Morris group, which showed that even with spurious rewards, Quen models can learn. Okay. Loss function, we achieve stable training without any KL-based regularization, different from the de facto AlShift community. This is also quite interesting. Scaling up training data. They identify that scaling up is crucial while training on limited academic data sets like maths leads to quick performance plateaus. All right. This is also an interesting point. Uh, this is also an interesting point. I guess I'll get to the figures when they talk about it. Experiments, they present comprehensive experimental results and analysis of our open regional zero models. We begin by the training setup and hyperparameters, followed by an in-depth analysis of training results, a typo, and application studies. Finally, we discuss the evaluation results. Training results and hyperparameters. We initialize both the policy and critic network with Qwen 2.5 base models. If you're not familiar with PPO, if you're only familiar with GRPO, due to R10, then sorry, due to R1, then the main difference between PPO and GRPO is that GRPO does not have a critic model, which is like a separate model which is used for predicting your advantage, essentially, and giving you like, uh, yeah. So you use the value model for estimating like a baseline thing, but in the GRPO setting, you estimate that using the things you sample and not via an extra model. So the value head is randomly initialized. The policy and critic do not share weights during training. For both policy and critic network, they employ Adam. Mhm. The learning rates are these. The learning rate schedule is about constant. Each generation contains 128 unique prompts sampled from the dataset and generating 64 responses per prompt. Temperature and top B both set to 1. To maintain training stability, they implement strict on policy optimization where each generation corresponds to exactly one optimization step. So this is interesting. So typically what people do is they first do rollout where they generate a bunch of traces. Then they might do multiple steps of learning over it. And then the first step is on policy. But as soon as you perform even a single update, the data is now off policy. But people think of it as being decently close, so they still use it. But what they say is that they outright remove it. So they outright sample after each step. The critic network being less sensitive to off-policy update processes the experience in 12 mini batches, effectively performing 12 optimization steps per iteration. Okay, so for the critic network, they don't do this. The critic network is basically like the value head, which predicts like a value estimate for the state. They apply batch level advantage normalization and training. For the be variant, they introduce additional annealing training stage inspired by, yeah, like mid training stuff. Specifically, they utilize the mind challenging prompts and apply a linear decay schedule to the learning rate, reducing it to this value over 1,000 steps. The targeted training phase is explicitly designed to improve the model's capability. Notably, our training process operates stably over without any care-related regularization terms or entropy bonuses, demonstrating that vanilla PPO can achieve stable training without these commonly used stabilization techniques. To comprehensively evaluate our model's reasoning capabilities, we conduct experiments on diverse benchmarks spanning mathematical reasoning and general problem solving. These include AIME 2024, 2025. Okay, so these are like just withheld datasets. Now, training results. Figure 2 shows that training reward and average response length for both these models, while figure 5 shows the reward accuracy and average response length curves. The training reward curve and the response length curves represent the average reward of the generated response and the average length of the generated responses. We observe consistent improvement in these metrics. I don't know if having longer responses is better, but I guess that is what training models aim for, and the sort of thing that longer traces are correlated with better answers, which I think people have shown to not be true as well, because these models tend to overthink. But yeah, very cool. Let's go to the figures again. Okay, so we already had a look at this figure, and then I think this said figure 5, which I believe is the next figure. Yes. So I believe orange is the response length, and blue is reward. The reward goes up, response length also goes up. But reward sort of starts to plateau a bit, I guess. Okay. Yeah. Quality analysis. Here we provide some qualitative analysis to analyze models' reflection capabilities and observe the aha moment like DeepSeek R10. They identify 5 representation reflection patterns where it rejects the alternative and however, following a methodology similar to 21, post 21, demystifying long. Ah, looks interesting. I'll take a look at that as well later. To count the number of responses containing any of these patterns as reflection responses and identify the average correct reflection length, the length of response containing reflection patterns. As shown in figure 6, the average uh, correct reflection length consistently exceeds the average response length, indicating that responses containing reflection patterns utilize more thinking time. A particularly noteworthy phenomenon emerges around step 680, where we observe a simultaneous distribution in 3 metrics: reward, average correct reflection length, and average response length. Through inspection of model outputs before and after, they achieve qualitatively more pronounced reflection patterns. Ah, this is super interesting. This is figure 6. This is the aha moment, and then after this, you see like a spike. Hmm, pretty cool. Appellation. We present appellation studies over key training strategies and hyperparameters. So they try a bunch of lambda combinations. Lambda 1 performs best. Specifically in the training reward, lambda 1 curves rise quickly in the early stage and remain stable, finally converging to about 0.8, while lambda 0.95 curve rise slowly and fluctuate. In the response length, the lambda 1 curve maintains a reasonable level during the training process, while lambda 0.95 curve shows unstable trend leading to PPO learning instability. These results indicate that GAE1 can better balance the training stability and generation quality. Moreover, discount factor gamma set to 1 also has significant impact. Less than 1 will result in penalty for long-term reward, leading to decrease in response length. Ah, makes sense. I would I would have liked if they had papers for this. Okay, they have a Notion page. Okay, I'll yeah look it up later. Constraint analysis, we evaluate different combinations of KL loss and KL penalty. Oh, also they have the different lambda. Oh, so 0.95 is. Oh, wow. It's very bad, which is very surprising to me. And then, uh, okay, what if you use KL and if you don't use KL, since a lot are conventional, moving both KL loss and KL penalty yields optimal training stability. And these things slow it down but also consume computational resources, but which would be better used for reward optimization. So without KL is this, KL loss and KL reward shaping. Yeah, much below it. Data scale, they also try like different sample sizes. Uh, Larger data scale leads to better results. So 57K versus 7.5K. Hmm, interesting. I guess it's also a question of is it just the scale or the diversity as well? And what if you train on smaller models? They try that as well. I mean, improves reasoning capabilities even at very small models. This is figure 10. Okay, so yeah, this is, I mean, the accuracy is nothing significant. It's like 3%, but still, uh, uh, who would have expected like a GPT to Excel parameter size model? Those, of course, much stronger to get even 3% on AIME one day. I guess AIME wasn't even there back then, so people never had any expectations. In Alfredo, we experiments, open reason zero, achieves good performance, blah blah blah. We evaluate the training dynamics, and yeah, it's stable. Length increases. There's fluctuations, but they don't affect. Deeper work is warranted, of course, to gain deeper insights. The accuracy generally shows a steady increase in training. Notably, we observe an interesting emergent phenomenon during evaluation where both reward and response tend to exhibit sudden step function like increase at certain points, which they refer to step moments. I guess since the aha moment thing came out, everyone now has to coin at least one moment. Finally, we present results on yeah these comprehensive benchmark suite. Conclusion is, I guess, again the same thing. They recall the bitter lesson. If you haven't read the bitter lesson below, it's very good. It's by Sutton, who's a Turing Award winner for his RL work. I'm not sure if it. I'm pretty sure it was his RL work, but I'm not sure if it was for something else apart from his RL work. He's also like the author of the very famous RL book. Uh, their future work is data scaling, model scaling, test time scaling, uh, multi-turn interaction, and scenario scaling. So, what if you have very different scenarios for acknowledgements, infrastructure by step one, and single. Okay, yeah, really cool. More results and sampling parameters for, I think this might be for the rollout phase, right? Because why else would you? Yeah, this is probably for the rollout phase. Okay, yeah, really cool. I'll just look at the, hmm, if you have C and Chinese data, that does not help, or it's like similar. What is US update step model in each generation step? Okay, so if you do 8 updates per generation, it sort of starts to fall. I think this is like the of policy thing, and the reward is yeah, update reduction step one is much better. We compare different sampling strategies, and what defined as lambda one, lambda point 0.9. I'm curious how did they pick these things? What they find is that basic sampling strategy works well. Okay, more ablations over the losses. They show that this configuration shows the most stable performance. All right, yeah, really cool stuff overall. Yeah, I'll probably now cover the speed 1.5 thinking paper at some point. Maybe today, I don't know. But yeah, see you guys next time.